Sorry guys, before as you're about to watch this video now, I made just a minor mistake up at Kaleni on it at the beginning. What I wanted to say there is that Ohm's law in a DC circuit, guys. What I wanted to say is that in an AC circuit, let me put it like this. In an AC circuit, Ohm's law cannot be defined as V over R. Okay, that is in an AC circuit, guys. In an AC circuit where the source is an AC, nah? Because with an AC we have to take into account other forms of the opposition to current, which is the inductive reactance and the capacitive reactance, because both these two values are dependent on frequency, as you'll see as I'm explaining in this video. Okay, I made just a mistake when I was starting the video, so please mind that. So in an AC circuit, guys, Ohm's law is defined as V over the impedance. The impedance taking into account, the impedance takes into account the resistance, the inductive reactance, and the capacitive reactance. Because with AC, we must take all forms of opposition to the current flow into account. Hey guys. Firstly, I want to greet you guys in this new trimester. I want to congratulate students who did well in their respective ends. Congratulations, guys. Now, I wanted to assist you again this trimester. Yeah. So I've been listening to your comments. I love your comments, by the way. Today I'll be looking at industrial electronics, which is the first lesson of the book. We'll be doing AC circuits. Okay, guys, before I start doing AC circuits, I need for us to understand this, guys. When we talk of the opposition to current flow, which is we call the ohms or the resistance. When it comes to AC, we must understand one thing, guys. We are not only with DC, the only opposition you get is the resistance. But with AC, you start encountering another form of resistance, which we call reactance. Okay, the reactance, let's say, let me write these two reactances down separately. So the first reactance is the inductive reactance, which opposes the current flow. Hence, we use the unit of ohms. Okay, then another reactance is the capacitive reactance. Okay, the capacitive reactance is also measured in ohms. Okay, with AC, guys, you start experiencing opposition to current flow due to the inductance of an inductor and the capacitance of a capacitor. Okay, as we can see, both these two reactances exist because of frequency. They are dependent on frequency. Okay, in an DC circuit, guys, the reactance is equals to 0 because with a DC supply, the frequency of a DC supply is 0. because a DC gives you a constant value of current and voltage. It doesn't fluctuate. So we don't experience reactance when we're talking of a DC circuit. The only form of opposition to current flow that we experience is resistance alone. Okay. Now, guys, we have to model now our Ohm's law. Yeah, but we have to modify our Ohm's law. Our Ohm's law is no longer gonna say I is equals to V over R. Okay, okay. This is incorrect in a DC circuit because in a DC circuit, there can be three forms of opposition to current flow. That is the resistance, inductive reactance, um, the capacitive reactance. So we must also account for reactance simply due to the fact that an AC circuit has frequency, and both these type of reactances, which is the inductive reactance and the capacitive reactance, are dependent on frequency. So the correct way to modify this Ohm's law is to say V is equals to O is V you're sorry, I is equals to V over Z, guys. V over Z. So now we are taking into account the reactances of a circuit. Okay, we are taking into account the total opposition of a circuit. So guys, as you can see, the first topic I'm gonna start on here is um, series RLC circuit. So I'm gonna start with a series RLC circuit, guys. Okay, so with a series RLC circuit, let us draw it down. Sorry guys, I'm using my driver's license. I misplaced my ruler somewhere. Sorry. So we have a resistor, we have an inductor, then we have a capacitor. That is why we call it a series RLC circuit. Okay. Now let us remember this is an AC circuit, meaning guys, my source is an AC source, maybe an AC generator, ESK, any source that can give me maybe an inverter, any source that will give me an AC output. Okay, so um, here is our total voltage. Because it's AC, it possesses frequency. Okay, possesses frequency here is my AC voltage at a certain frequency. In most cases, it's 50 hertz because that is the standard voltage in this country. That is a standard voltage in South Africa. That is 50 hertz. Okay, guys, we see here we have the resistance. We have inductive reactance. That is another opposition to current flow. Okay, we have sorry, that is inductive. I said that is inductive reactance. Then we have capacitive reactance. We must take into account, guys, the reactance because now with an AC source, we have frequency and the reactance is frequency dependent. We didn't take into account the the reactance in a DC circuit because simply because the frequency of a what? Of a DC circuit is 0. So if I were to calculate inductive reactance in a DC circuit, it would be 2 pi times 0 times L, whatever inductance that was. And then I would get what? 0 ohms. So I can discredit the the inductive reactance in a DC circuit. Same as if the capacitive reactance, I would have 1 over 2 pi times 0 times C, whatever the capacitance is. You see that anything multiplied by 0 is what? 0, guys. Okay, it is 0. Okay, now we are looking at an AC circuit. An AC circuit that has resistance, an inductor, and a capacitor. Okay, so guys, there are three circuit components that are causing an opposition to current flow. Okay, we know um the voltage according to Ohm's law is a function of the current times that opposition. Okay, so basically the resistance will cause a voltage drop, okay, due to the resistance of the circuit. Okay, now even the the inductor will cause a voltage drop due to the inductive reactance, guys. Okay, because now the inductor is opposing current because it is an AC circuit. We have an inductive reactance. Same goes for the capacitor. It will also cause a voltage drop, okay, due to the capacitive what reactance of what the circuit. So we see from here now that we have three voltage drops. Okay, the first one being the voltage due to the resistance. Okay, then the next one is a voltage drop due to the inductive reactance of the inductor. Okay, the next voltage drop is due to the capacitive reactance of the capacitor. Okay, okay, nothing has changed with regards to Ohm's law, guys, as we can see. Okay, nothing has changed. If I wanted to calculate the total current in the circuit, that would be VT over the impedance. The total what? The total impedance. In an AC circuit, we no longer talk of only the resistance. Okay, there are other two forms of opposition to current flow. That is the inductive reactance and the capacitive reactance. We must also account for them because now we have frequency, and the opposition that these two components, which is the inductor and the capacitor, offers to the current flow is dependent on the frequency of the supply. Okay, okay, here is my I total. Okay, here is my I current through the resistor. Here is the current through the inductor, current through the capacitor, and we can safely say, because this is a series circuit, guys, this is a series circuit, sorry, there's only one path for current to flow. There's only one path for current to flow. Okay, there's only one path for current to flow. Therefore, the current through every part of the circuit through every part of the circuit is the same. The current through the inductor is the same as the current through the capacitor, and is the same as the current through the inductor. Okay, okay, guys. How do we then calculate the total opposition to current flow while including the resistance and the reactances? Okay, there's a field in mathematics that helps us solve this engineering problem, guys. That is using complex numbers. Definitely by now at this level, you know what we use complex numbers for. Okay, because guys, AC values or AC quantities, you may say, whether it's AC voltage or whether it's AC current, it has magnitude, has both magnitude and direction. We can represent it as a phasor or a vector. Okay, you will see when I start talking about uh, vector diagrams, because when you are analyzing a AC circuit, it is critically important to know, uh, understand, and how to interpret the phasor diagram, guys, of which is that is also something we're going to go through in this lesson today. Okay, the impedance, okay, is calculated as follows. It is Z, which is the impedance. I'm talking of the impedance, guys. I'm talking of the impedance of a what? Series RLC circuit. We're going to have first, sorry, we're going to have first what? Sorry, the resistance plus uh, J, which is the imaginary number, then XL minus XC. Okay, that values is measured in ohms. Now, you can see, guys, for any series RLC circuit, that is how you calculate your total impedance. It doesn't matter, guys. The sign will sort out itself. It doesn't matter whether XL or let me say XC is greater than XL. It doesn't matter. The sign with this formula, it will sort itself out. Okay, so this is how we calculate the total what? Impedance. And guys, because we are working with complex numbers, when you are writing the value of the value of the final value. Maybe it doesn't matter, maybe it's a current value, or you are calculating the voltage value, or the impedance value. Please, guys, you always write your final answer in what? Your final answer in polar form. Okay, in polar form, because the polar form, remember, how do you calculate the absolute value of a phasor in complex mathematics? You look at the value in what? In polar form. Then the polar form will give you the actual value. So here we write this, the final answer of this in polar form. Then we'll get the actual value of the impedance and the angle. Okay, or maybe I was calculating current, I'll get the actual value of current and the phase angle. Or maybe I was calculating the voltage, in polar form, I'll get the actual value of the voltage and the phase angle. We only consider, we only, what I want to say, we only convert to a rectangular when we're doing calculation. Maybe I want to add two complex values. Then I know when I'm performing addition, my values should be in rectangular form. Okay, so my values should be in rectangular form.